Hello and welcome to this video. In this video we are going to be designing the control unit. So let's create a new circuit. Control unit. Okay, so first of all we need to get our inputs. Our inputs will be the instruction, the carry flag, the zero flag, the negative flag, and the clock. So we need an input for the instruction, carry flag, zero flag, negative flag, and the clock. The instruction is going to be 16 bits binary. And this is our carry flag. Alright, no spaces. Then we have our 0 and negative. And then we have our clock. Okay, so in here we are going to have a register to store our instructions. And the write enable of this register, we are going to connect it to a channel we would call fetch. And this fetch would be ORed with another channel we would call get next. Watch the names very carefully, we would need them later on. So we are ORing these two. And that goes into our write enable. So we are going to have a splitter. Let's see. There we go. It's going to be splitting 16 bits. Appearance right-handed. Okay, so we have a splitter in. This splitter is going to give us every individual bit from our. So our splitter gives us every bit from our instruction, and let's extend those lines. And now we are going to group them based on our instruction set. So we are going to have splitters connected to every set of 4. Let's do one more. There we go. So to every set of 4, we connect. And now we are going to name them based on our instruction set. So we have opcode. So we get a tunnel. This will be opcode. And we have a tunnel for RS1. Then we would have a tunnel for RS2. Then we'd have a final tunnel for RT. Okay, so now we are going to divide ALU opcode from the general opcode. So let's get a splitter, put that there, have a face south, center it, and this will be 3 bits. Okay, so in this step we are going to have a demultiplexer for select bits because we are dealing with 16 operations. Data bits will be just 1. We are going to get up to a constant. Okay. And the select here is going to be based on our opcode. So that's our opcode. That should be 4 bits. There we go. Okay, so you can even see that since our opcode is on 0, 0 is selected. But we are going to do something a little different here. We are not going to be thinking about the ALU operations because those are implemented in the ALU exactly. We're only going to be concerned with the non-ALU operations like the moves, the loads, the jumps, store, fetch, those ones. So let's extend Okay, and we are going to hook each of them up to a tunnel with the name of the instruction. So this we said would be our move R. Then we would have another connected to our move I. And after move I, we have load and store. So we have load, store. And after load and store, we have the three jumps: jump, jump 0, jump negative. And we end this with fetch or no up. Basically the same thing in this architecture. And we are going to have a little extension here. We are going to hook it up to another tunnel. This is going to be called SOP, that is operation, and we are just going to have a knot. Where's the knot? There we go. Okay, now you can see in this case that the SOP only turns on when it's not a fetch. So if it's anything other than a fetch, it means it's an operation. Because remember, the fetch is also called the no op. So if it's a no op, then it's a no op. But if it's not a no op, then it is an op. So yeah, we would need that later. So now let's work on our output control lines. So if you remember, in the main circuit we had a bunch of manually controlled signals. We are going to have them thrown all over here this time. So let's get to it. Oh, hold on. So yeah, with the ALU opcode we have to do that. Didn't realize I hadn't done that. Let's see. Oh wait, this should be 3 and there we go. Okay, we should have 0 on the last. So let's change that. Bit 0 should be 2 and this should be 0. Okay. And we are going to connect that to a tunnel we are going to call ALU OPC. That's ALU opcode. Let's have that pointing south. And this should have 3 data bits. There we go. And before we move on, we just want to do another thing we want to check if it's an ALU operation. And how do we do that? We know that all control unit based operations have a 1 at the beginning. That is, they start from 8 and they end at 15. So we are going to simply check this bit. If this bit is a high or a 1, we know that it's not an ALU operation. So let's get our NOT gate. We're going to press that into a tunnel. So what we're going to call this tunnel is simply ALU. There we go. And per our spec, we know that when all bits are high, it's a halt operation. So we simply need to take every single bit and end it. Pretty simple. So let's drop this, drop that. And let's get an AND gate. Let's have that facing south. We're expecting 16 inputs. That's right. Narrow. Okay. And so you just have to hook them up. Okay, let's just move this down a bit. Yeah, so the purpose of the halt operation is basically to turn the processor off. So say you wanted to like how typical computers, you have a shutdown which shuts down everything. Yeah, it's something like that. And so we are going to have this going down to a tunnel, and that tunnel is going to be called halt. Okay, so now we can work on our outputs, that is our control lines. So let's come to this side of things. Now for our control lines, let's get a splitter, and the splitter is going to split into our control lines. So we are going to have a splitter. Okay. Appearance is okay. Spacing, let's have it double spaced. In fact, let's have it triple spaced. Yeah. And so fan out and bit width in. We want it to be from 0 to 28. So that's 29. Let's see. That's 0 to 20. Okay, I need to bring it lower. Yeah, 0 to 28. And so we are going to hook every one of them to outputs. So we'd have these three. Now this is arranged from least significant bit to most significant bit. Okay. These three are going to represent our ALU opcode. So let's get a split face west. Let's center that. 3, 3. Let's have a triple spaced. Put that in, channel it. And like I said, this is our ALU opcode. So ALU underscore OPC. Alright, so our next is going to be for our MBR. So we would have our MBR IDWE. Right. That was MBR INWE. Okay. After that, we are going to put our halt. Following that, oh wait, hold on. I just realized I'm supposed to be putting outputs here. Should be 3. Sorry about that. This should be 3. Okay. And then I would name the outputs. Yeah. And okay, so following that, we're going to have IM OE. Let's see, let's go back to main and let's check our control lines. Okay, so let's have IMOE. Now you can actually arrange them in any order. You just have to take note of the order you're arranging them in. You're going to have ALU write enable and ALU output enable. So this will be ALU write enable, ALU output enable. Then we're going to have PC load, PC count enable, and then PC output enable. That's these ones here: PC load, PC count enable, PC output enable. And now we want memory address registers. So we have MARWE, MAROE. Now we would want to move on to RAM. So we have RAM write enable, RAM output enable. Oh, we need to do that. Now I want you to understand that every line we are connecting is going to represent what we're doing manually in the main circuit. Just that this time it won't be done manually, it will be handled by the computer. I mean, otherwise it's not really a computer anyway. Then we are going to have temporary address register write enable and output enable. So this will be TA write enable, and then we'd have TA output enable. Shift that a bit, yeah. After temporary address register, let's move on to so let's see. Okay, for our ALU we have R1W, R2W, so let's do those. This will be R1WE, and then we would have one for R2WE. Oh wait, there we go. After this, let's have MBL write enable, output enable, and all the other MBL stuff. So let's go back to main. So for MBL, we had the write enable, IN write enable, then we have the IN output enable and the EX output enable. So let's wire them up. I think we already did one earlier control unit. We did the IN write enable, so let's do the others. I think there were 3 others. Okay, so first let's have our write enable. Then we need to have output enables. Let me see, what did I call them? So we have EXOE. So EXOE, let's do that. And then we also had internal bus OE. Okay, so I think that should be the last one, right? Yeah. There we go. And after MBR, we would want set flags SF. Remember SF from the flag register. Then we would want our GPR selection to be done here. That's going to take 4 bits. So let's get a split. Face that west. We want 4 and 4N. And let's space that nicely. Okay, let me center plug them in. And this is going to be a GPR select. There should be 4 data bits. GPR SEL. Okay, so we are left with 2. That will be our GPR write enable and GPR output enable. Alright, so now we have our control lines set up. Let's continue a little bit more with the output circuit. So we are going to have a multiplexer here. This is going to have 29 data bits. It will have just one select bit here, and let's hook that there. For the 0 side of things, we are going to hook in a fetch value. So this is going to be a constant. It's supposed to be 29 bits. Yeah. Let's leave that in hex. I think that's the best. And then for the lower side, we are going to have a tunnel for our select lines. This should be 29 bits also. Okay. Now the selection of the max, we are going to have a NOR gate. Let's have that narrow face not, I guess. Yeah. Okay. And to this NOR gate, we are going to have the fetch we did earlier on one side. Come on. And on the other side, it's going to be a bit complex, but it will all make sense. So here we are going to have a tunnel in. Let's get next. And it's going to continue onto a max. So let's find the max. Should face west. For the 0, this we are going to need a constant. There we go. 0 is going to be just 0. And for 1 would be connected to our internal control bus. And our selection is going to be based on a tunnel we defined earlier is up. Okay, let's zoom out a bit and see. It's already starting to look a bit plenty. Yeah, it's going to get much more than this as we go along. So now we are going to actually implement the instructions. Right. So to do that, we are going to create a little circuit for counting. How it's going to work is you're going to have a latch, right? You're going to have a latch connected to a counter. Now, since this is a CISC CPU, a single instruction executes in multiple steps, and you want to be able to know which step you are on. So to do that, you are counting. You know that on the first step I should do this, on the second step I should do that, etc. So you're going to have a counter, but you wouldn't just want the counter to keep counting. You'd want the counter to count based on the number of steps for that particular instruction. And for each count, you'd want to change the select lines because different steps do different things, right? So let's implement our first instruction, the move R. So we had a clock earlier. Let's tunnel that because we are going to be needing it. And I'll just call that CLQ. Okay, so down here, tunnel face east. This is going to be our CLQ. And we write away. Alright, so we are going to pick up a flip-flop. We are going to hook it up to a counter in a very specific way. So I think we have a D flip-flop here. Do I want a D flip-flop? No, I would want an SR flip-flop. Let's see, can't I get an here SR? There we go. Let's zoom in a bit. And we would want a counter. There we go. So for our counter, we would want it to just be 2 bits. Should be a 2-bit counter. There we go. And it should end on 2. We are going to connect the output of the counter into the S of our flip-flop, as in this output. This output determines whether the count has reached the specified value. So when it hits to 1, it would make the S here 1. And let's clock this in. There we go. And we also need to clock this guy in. Enable here, we don't need that. And so we are also going to need a reset line. Let me create a tunnel for that. The reset line is basically to reset everything. So I'm going to call that reset. I think that's fine. So we are going to, the reset is going to connect it to the reset of every component, every memory component, I mean. So over here we have reset here. So basically the reset allows the control unit to reset everything regardless of wherever it is in whatever it was doing. Now we are almost done with our circuit here. One thing though is we have to make this falling edge very important. So the flip-flop should be a falling edge flip-flop. Okay, so let's calm down a bit. Now over here we are going to do some very interesting implementation. Let's get splitters. Should be wiring here. Face west. So we are expecting 29 and we are expecting 29 in also. So you're probably wondering why is it going to be interesting. So for every step we are actually going to be determining the ones and zeros we would have done manually. So if we wanted to move something from a register to another register, we are actually going to place how we would have done it by hand. We are going to have values for that. So in fact, let me get 2 constants. one is going to be of value 0 face south, and one is going to be 1 facing south also. Let's just drop them down. Okay, so now let's do some careful wiring. Let me zoom in on that. So we are going to connect the first 3 to 0, then we connect the next one to a 1. So 0, all these, and then this goes to a 1. Then we 0 the rest all the way here. So 19 gets a 1. Then we 0, we are going to 0, 20, 21, and 22. Now 23, 24, 25, 26, these are GPL select. So we are not going to just 0 them, we are going to hook them up. These should go to, they should come from RS1. That should be 4 bits, yeah. And yeah, so you guys, we are going to need a splitter. Let me do that here. Centered. You're expecting 4 and 4. And in the RS1. And for the last two, we are going to have this on and this off. Okay. And we are not done yet, so we need a controlled buffer at the end of this. The reason is you don't just want to write the output immediately, you'd want to control when the output gets written. So this will be a 29-bit control buffer. Let's space there a bit. And this is going to move into a tunnel we are going to call move R1, as in move R step 1. Yeah, and this is going to be 29 bits, and this is going to be controlled by move R. So if the currently selected operation is not a move R, then there is no use to write anything anywhere. That's why we have this here. Let me just space that a bit. Okay, so that's step 1. Let's move on to step 2. So step 2 is going to be very similar, so let me just duplicate this over here. First off, let me kill some lines. Okay. Okay, we may even just have to leave this, so let's see. For step 2, okay, so step 2 is going to have RS1. This should rather be RS2. Step 1 rather should be RS2 because you're moving the contents of the second into the first. So we take the data from the second first before moving into the first. And we are going to have these differently. So this would be on, whereas we have, and then we are going to have 21 and 22 on. So let me, there we go. And these are going to be off all the way to the top. There we go. Okay, so let's take a look at what we've done. Let me move everything, Control A to select everything and just move them. Okay, so we are not done though. You notice our counter, we are not actually fetching the value anywhere for anything. So yeah, we are not done. We are going to have a Dmax. This dmax is going to have 4 states, so we would need 2 select bits, and it's going to be getting its value from here to 1. So that should be, let me see that. Oh no, let me undo that. This should rather be the select. Yeah, there we go. And the value we are passing to it will be a constant 1. Yeah, so since the count is currently 0, you can see it's 0 here. As in 0 is selected. Let me zoom in a bit. Okay, so what we are going to do now is, so one more thing, this should be moved out to, since it's the second step, right? So we are going to, for step 0, you are going to want to move the first step, that is R1, into our select lines. So let me just show you how that would look like. East, move R1. This is expected to be 29 bits. And we are going to have another tunnel for our select lines, also expected to be 29 bits. But we are not just going to throw it in there, everything is controlled around here. A 29 bit controlled buffer. Okay, so let me copy this. Okay, now what enables this? That's where this comes in. So let's move on to our next step. Our next step would be for move out to. Let me move this a bit and duplicate this. Okay, and the final step is going to be a fetch. So every operation's last step is to fetch the next operation, right? So right now we do not have the value for that. It's going to be the same value that will be here. So let me cut this. Let's have a tunnel. And I'm going to call this, okay, I want this to be different from the fetch operation, so I'm going to call this well, okay, let me just call this FTH, I guess. And so let's define FTH. Let's get a constant. This should be a 29-bit constant. And that should be FTH. FTH should be 29 bits. There we go. What's the issue here? Oh, here's 1 bit, 29. There we go. So later on, when we determine the lines needed for a fetch, we'll just come here and change it. So let's go back here, and we'd have a tunnel pointing east. You'd have select lines, and we are basically going to move a fetch into a select line. Let me do that too. It should also be 29 bits. The name of this would be FTH. There we go. controlled buffer as usual. That should be a 29-bit controlled buffer. And this is going to connect it to our DMAX here. Okay. Right, so now there's just a little bit of wiring to be done. So let's move. Now this shouldn't be plugged in directly because we want to control its clocking. So let's have a controlled buffer, and this buffer is going to be controlled by this value, and then we are going to have the clock in. Quite a nice circuit. Okay, so I think this should be all for the move R. We'll definitely test everything in the end. So after this, we are going to be implementing the move I.